Okay, hello everybody to this week's ISGC seminar talk. This week's speaker is Marius Oancea. He received the PhD in 2021 from the University of Potsdam, where he performed his research at the Albert Einstein Institute, and since 2022 is a postdoc at the University of Vienna. Thank you, Marius, for agreeing to give this talk. The stage is yours.
Oh, thanks for the nice introduction, and also thanks for the invitation and for organizing this seminar. So today I want to talk a bit about polarization-dependent gravitational lensing and what we mean by this. This is related to some previous projects, and there are some previous papers regarding this already out. And also, we currently have an ongoing research grant where we want to develop this even further. And I also tell you briefly what we want to do next later on after in results. Okay, so let me start with an introduction. So just let me briefly review what I mean by gravitational lensing in this context. In particular, I'm interested in effects beyond the usual geometric optics setup. So let's quickly review what I guess most of you are familiar and what we usually consider when we do gravitational lensing. Basically, we describe the propagation of light in the geometric optics approximation. So some of the underlying features of this is that we are mostly interested in this case, in the infinite frequency limit or in a very, very high frequency limit for our electromagnetic waves. And then in this setup, we approximate the propagation of electromagnetic waves by light rays that follow null geodesics in our spacetime. Also, generally within this traditional setup, polarization effects are generally neglected. Or if you want, you can, within geometric optics, you can take into account the polarization vector and then just parallelly transport it along the underlying null geodesics. So this is the usual setup of gravitational lensing, and this is a pretty good framework. We can describe a lot of things with this. In particular, as you see here, we can predict Einstein rings. This is like a weak regime of gravitational lensing where nevertheless we see the bending of light, but the gravitational fields along the paths of the geodesics are very, very weak, right? So this has been confirmed in many experiments, and we use this quite successfully. And on the other hand, we can also use this in a slightly different regime where the gravitational fields are now very, very strong. For example, to describe lensing around black holes and even black hole shadows. So this is where, again, we can confidently use the null geodesics, and this gives us a pretty good description of this sort of regimes. Now, the question is, how can we go beyond this? And also, why should we go beyond this? So first thing that we should remember is that both electromagnetic and gravitational waves, in general, these have finite frequencies. And also, maybe we don't want to neglect the polarization degree of freedom. So maybe in some scenarios or in some setups, taking into account polarization might become important. Okay, so now we're going to try to go a bit the usual geometrical optics setup that's usually employed in most of the gravitational lensing literature. And one question is, how should we do this? How should we incorporate higher order corrections to geometric optics? Or in other words, higher order corrections to the null geodesic equations. And the answer in general is that we're going to get what are called spin Hall effects. So these are some effects which modify a bit the geodesic equations by some higher order correction terms. But we are still in a regime where we're describing the propagation of light in terms of some rays, just modifying the geodesic equation to have some other equation. We still have some rays, and these are ODs are pretty manageable. And it's not yet a regime where we need wave optics, right? That would be an even better approximation that we can go to wave optics, but now we're in this intermediate regime where we're still in ray optics, but we're modifying a bit the rays to incorporate more effects, in particular the effect of polarization. Okay, so now let me tell you a bit what I mean by spin Hall effects, right? Because maybe some of you are not familiar with this. These effects are very common in optics and in condensed matter physics, but maybe not that common in general relativity. So let me briefly go through the main ideas. Basically, whenever we think of electromagnetic and gravitational waves or wave packets of these waves, these are generally going to carry some non-zero amount of intrinsic angular momentum, right? You can think of this as related to the polarization of these waves, or you can think of these two fields as being the electromagnetic field, the spin one field, and then the gravitational linearized gravity being as a spin two field. So then there's some intrinsic notion of angular momentum that you're going to have associated with these fields. So then what generally happens is in certain regimes of approximation, you get what are called spin orbit couplings. So you get a mutual interaction between the internal, or in other words, the angular momentum degree of freedom and the external degree of freedoms. By external degree of freedoms, I mean, for example, if you consider a wave packet, this would be like the average position or the average momentum of the wave packet as a whole. So in general, we get this coupling between angular momentum and position and momentum degrees of freedom for our wave packet. This is something that we don't see in geometric optics, but we see it if we go a bit beyond geometric optics by including higher order corrections to geometric optics. Okay, so now as a consequence of this mechanism, we generally get spin Hall effects where we obtain that the wave packets are now going to follow spin-dependent trajectories. You can think of this as being geodesic equations with some spin-dependent additional correction term. Okay, so this is what we generally mean by spin Hall effects. These general features are valid even in other, not only in the case of gravity, but also in optics or in condensed matter physics and in other areas of physics as well. So this is quite general for these effects. Now, what's important is that these effects have been experimentally observed for electrons in many condensed matter systems and also for electromagnetic waves in materials with inhomogeneous refractive index. And even just beyond the pure theoretical interest, these effects have led to many technological developments and many things like this, particularly in condensed matter physics. So now a natural question that we can ask is if we also have something similar in gravity, where electromagnetic waves, gravitational waves, or maybe even electrons described by Dirac fields, if these sorts of wave packets are going to experience something like a spin Hall effect when they propagate in the gravitational field. A motivation behind this is the analogy with optics. Maybe some of you know that in general, we can think of space-time where you have some gravitational field and you have some inhomogeneity of this gravitational field. You can think of this in an analog way as a material with some inhomogeneous refractive index. And then since we see the spin Hall effects in the optics case, then it's also natural to expect that such effects are also going to occur when you have some inhomogeneity in our gravitational field. Okay, so before going to the gravitational effects, let me say just a bit more about the spin Hall effect of light in optics. So this has been measured, for example, in 2008, so not so long ago. It has been measured in the following setup over here. Here you have a beam of linearly polarized electromagnetic waves. So you can think of this linear polarized wave as a superposition of equal amounts of the two circular polarizations. And then this beam is sent through the cylinder, and what you see here is that this beam splits into two parts. These are the components of opposite circular polarization, right? So here you have one circular polarization, here you have the opposite one, and then you see after some time you get this finite separation between the two beams. Basically, this is the polarization-dependent propagation of light, which describes the spin Hall effect of light in optics. Okay, so now one question is, how do people generally describe this in optics? And I can summarize that quite quickly over here. Basically, they start from Maxwell's equations, and then they consider the geometrical optics approximation, but they go a bit beyond this and they consider some higher order corrections to geometric optics. And there are like different ways and multiple ways of doing this and arriving at the same result. I don't want to go into the details. But what you get by doing this is, on one hand, from geometric optics, you get these equations over here, only with the terms in black. So these are the usual ray equations that you get whenever you have light propagating in the geometric optics limit in some inhomogeneous medium, right? So you see here the effect of the inhomogeneous medium. This is what is going to bend the light rays in the medium. And then if you also include these higher order corrections and you properly include the spin orbit coupling mechanism, then what you get on top of this, you get this additional correction term in red over here. So this is basically the main term which drives the spin Hall effect of light in optics. So let's break down a bit this term. So we have epsilon over here. You can think of epsilon as the wavelength. We have S over here. So S is going to be plus minus 1, depending on the state of polarization. So then the state of polarization is going to control the direction of this term. And then you have these other terms which depend on the momentum. And basically, if you want, you can replace this P dot, you can replace it with an nabla N. So you see, you need an inhomogeneous term in order to get the effect over here. Okay, so these are the main features of the effect in optics. And now the question is, how does this work in a curved space-time when we have electromagnetic waves or gravitational waves propagating in some inhomogeneous space-time, right? And basically, you get what are called spin Hall effects. And these have been described in particular in these papers. So here we did the spin Hall effect of light, and in the second paper, we did the same thing, but for linearized gravity. And then in this third paper, we discussed a bit some more details and some more properties of the equations. There are also many other papers that I'm not mentioning here. This has been also derived by many other authors using slightly different methods. It has also been applied to Dirac fields. You also get an effect in that case, and then there are like various extensions of these results over here. So to quickly summarize what we get, let's look at how the ray equations that describe the gravitational spin Hall effect look. So basically, these are the equations that you get. Now you see, maybe you probably recognize again this first terms over here. This is just the terms that you normally get in a Hamiltonian formulation of the geodesic equations, right? So this is the usual setup. This describes geodesics, and in particular null geodesics, if we're talking about light. And then on top of this, we get some correction terms. Now, what's a bit different from optics, in optics, we only got an extra term in the x dot equation. Now, we also have an extra term in the p dot equation. Now, let's look a bit closely at these terms. So we have this S, this capital S in both terms. This is basically a spin tensor, and it describes the amount of angular momentum carried by the wave packet. Okay, we have some P's, some momenta, and we also have this T. So what is this T? The T is basically the forward velocity of an observer with respect to which you define the energy centroid of the wave packet, right? So you have the wave packet as a whole, and then you want an effective point particle description of the wave packet. How do you go to that? One way of doing that is to say, okay, instead of looking at the whole wave packet, I just want to look at the center of energy of that wave packet. But in order to define the center of energy, I need to introduce an observer. So with respect to which observer do I measure energies? And again, this is where this T comes from, is by introducing this observer with respect to which we define the energy center of the wave packet. Okay, so this is why this shows up in the equation, because there's an intrinsic dependence on the center of energy, on the choice of observer that we introduce over here. And I'll show you a bit later, there are ways to physically motivate this choice when you take particular examples. Okay, now if you look at the definition of the spin tensor over here, we see the epsilon, which again, you can think of the epsilon as the wavelength, and we also see the S, right? Where S is again, ±1 for circularly polarized electromagnetic waves. But if you look at the gravitational case, then you get the same equations, but with S equal ±2 for circularly polarized, linearized gravitational waves. And this is just because one field is a spin 1 field and the other field is a spin 2 field. So naturally, it carries double the amount of angular momentum. Now, the other thing that you see over here is the Riemann tensor. So this is on top of what we see in optics. We have this coupling to the curvature of space-time. Now, also looking at this term in particular over here, maybe you vaguely recognize this term from somewhere else, and in particular from the MPD equations. So the MPD equations are these very general equations meant to describe the spinning particles in general relativity. They are generally derived under very mild assumptions. So basically, you just need to conserve the stress energy tensor, and also you need to assume some sort of compact support for your matter that you're describing with that stress energy tensor. So in principle, the MPD equations are very, very general. We have them written over here, and they can describe very general types of matter, even though in the literature, these equations are mostly used to describe massive spinning particles. So most of the literature focuses on that, but nevertheless, you can also use the equations to describe massless spinning particles, as we do with the spin Hall equations. Now, what's important is that the spin Hall equations that I showed you before are just a special case of the MPD equations that we have over here. And in particular, to go from the MPD equations to the spin Hall equations, we need to do the following. First, we need to impose a spin supplementary condition. This is S dot T equals 0. This is where, again, the time-like vector T comes into play again. And this is basically related to what I told you before. This spin supplementary condition is basically introducing a way in which you define your energy centroid, or say your center of energy for your wave packet. You need to specify an observer which measures the energy, and then you define the center of energy of the wave packet with respect to that observer. And this is exactly what the spin supplementary condition does for you in the MPD case, right? So it fixes the notion of centroid relative to a choice of time-like observer T. So this is one condition we need to impose. Then we also need to fix the parametrization such that this relation holds. So this is just a particular choice of parametrization. There's no loss of generality with working with one parametrization of the word line or another. And then we also need to impose some initial conditions. We need to impose that the momentum is initially null, and the momentum is also orthogonal to S. Okay? So first one, the momentum being null. This is just because we want to describe massless spinning particles, right? As we would do with null geodesics, you initially impose this null, and what you get from the equation is that this is going to remain null during the evolution. The second condition, sometimes this S dot P equals 0 is used as a spin supplementary condition in the massive case, but here we cannot do that because if P is a null vector, then this is not a spin supplementary condition. It's not going to fix your definition of energy centroid. So then here, this is not a spin supplementary condition, but a physical constraint on the type of angular momentum that you're considering. Basically, by imposing this, we're saying, okay, I'm only considering wave packets which have longitudinal angular momentum, where if you go from the spin tensor to a spin vector, then that vector is going to be aligned with P, or anti-aligned with P, basically. Okay, and then this second condition over here, this just fixes the magnitude of the spin tensor, basically. So if we impose these conditions on the MPD equation, then basically we recover the spin-Hall equations that I introduced before. Now, why is this important and why do I even mention it? First of all, because there's a lot of literature on the MPD equations, and these equations have been studied in great detail, and we know a lot of results which generally hold for the MPD equation. So then this means that we can use these known results and also apply them in the case of the spin-Hall equations. Just to give you one example, if you consider the MPD equations in certain space-times, let's say you consider it in some black hole spacetime like the Kerr spacetime, then there are known conserved quantities for these equations, generalizing the usual ones where you have killing vectors and also generalizing Carter's constant when you have a killing tensor. Basically, now we also get the same for the spin-Hall equations. We're going to have the same conserved quantities for the spin-Hall equations and also the generalized Carter's constant and so on. Okay, we had a recent paper about this just at the end of last year where we discussed the conserved quantities for the spin-Hall equations and then also the resulting notion of complete integrability that you get for these equations when you have these conserved quantities. Okay, so then this is why this connection is important. And before going on, I can give you a brief numerical example of how the spin-Hall effect looks, just to give you some intuition of what to expect next. So let's consider a Schwarzschild black hole over here, and then I can place a source of light over here. And from this source, I emit different rays with the same initial conditions. First, let me emit a ray with S equals 0. Basically, this is a geodesic, right? So if I put S equals 0, then I'm canceling all the correction terms and I'm left with the null geodesics. So then you get the green trajectory over here. This is confined to the equatorial plane. It's just the usual null geodesic, and you see the usual type of light bending around the Schwarzschild black hole. Now, from the same point and with the same initial conditions, I now consider arrays with the spin-Hall equations, but now with little s equal plus 1 or minus 1. So these are going to correspond to rays of opposite circular polarization. Now what I see this off-plane deviations from the geodesic plane, basically. So this is how the spin-Hall effect of light in this very simple example comes into play. When compared to the null geodesic motion in Schwarzschild, then you get this off-plane deviations in a polarization-dependent way. The effect also scales linearly with frequency. So if you, it also scales linearly with wavelength. So if you increase the wavelength, then you get a larger effect. If you decrease the wavelength, then you get a smaller effect, basically. Okay, so this is, in a nutshell, the basic theory behind the spin-Hall equations in Kerr spacetime. And I think I try to transmit some basic intuition about how these equations work. Now, the main question is, how do we apply this in a gravitational lensing scenario? How can we use this to get polarization-dependent gravitational lensing? And most importantly, one question that we should ask ourselves is, where should we look for astrophysical signatures of the gravitational spin-Hall effect? Because normally, this being a subleading effect beyond geometric optics, this is generally expected to be very small. So it's natural to ask for astrophysical setups where we would somehow try to maximize our chances of seeing the effect. And basically, there are two components that we need to satisfy in order to get a significant effect. First, we want large wavelengths, because the effect scales linearly with wavelength. But also here there's a catch in the sense that we should keep in mind that while we want large wavelengths, we shouldn't push this too much, because after some point, the approximation under which the effect was derived is going to break down. So we're going to break down the beyond geometric optics approximation if we keep increasing the wavelength. So we don't want to push this too much, but still we want to have it as large as possible such that the approximation is still satisfied to some reasonable level. Okay? And then the second ingredient that we want are strong gravitational fields. In particular, you're going to get very, very small effects if you're in a weak gravitational field. Even though you get to see something like Einstein rings in that setup, you're not going to see any polarization-dependent corrections to the Einstein rings just because the fields along the trajectories are very, very small. Okay, so this second constraint is basically telling us we should try to go as close as possible to the event horizons of black holes, because that's where the gravitational fields are going to be the most strong. Okay, so then these two conditions already suggest a possible path. Basically, if we want to maximize the wavelength, if we just quickly think of what we can possibly observe with electromagnetic waves, this would be radio waves. So then wavelength is order centimeter or at best order meter. So that might not be that great. But then on the other hand, if we think about gravitational waves, then in this setup, the typical wavelengths that we observe are of the order of 1,000 kilometers or something in that range. So that's already 6 or 7 orders of magnitude much larger than what we have for electromagnetic waves. Okay, so then this immediately suggests a possible path and a possible astrophysical setup in which we might see this effect. Basically, we want to look at the strong field lensing of gravitational waves. And this is exactly what we did in these two papers over here. And I'm going to go a bit over the details of these two papers just now. So basically, we want a source of gravitational waves, which is located near another black hole. So where would this happen astrophysically? In principle, we might have a chance of seeing this if we consider what are called active galactic nuclei. So these are the regions close to the centers of certain galaxies where we have a very, very massive central black hole. And then you can have an environment in which you have all types of very extreme matter, and also you can also have smaller black holes and things like this. Importantly, what can occur in this sort of setup is you can have something like a system like over here, which is called a hierarchical triple. So this is a system where you have two black holes merging in the vicinity of a third black hole. So now, basically, the two merging black holes can act as a source of gravitational waves. And then the third black hole can act as a lens. So basically, you're emitting gravitational waves from over here, and then they get on their path to the observatory, they get lensed and they experience the very strong gravitational field of this third black hole. So this is the type of systems that we would want to describe, and we would want to see if the spin Hall effect for gravitational waves can be significant in such a setup. Okay. So now let me briefly tell you what we did in those two papers and what was our basic setup over there. So we consider strong lensing of gravitational waves in the following scenario. So first we consider a background Kerr black hole with mass m and spin a, and this is going to represent our lens. So you can think of this as a very, very large black hole. And then next to this very, very large black hole, we want to put a static source of gravitational wave very close to this large black hole. For example, you can think of this large black hole as being something like 10 to the power 4 or 10 to the power 5 solar masses, and then this static source of gravitational wave is going to be represented by two much smaller black holes, let's say of order 10 solar masses. Okay, so then effectively you can think of this source as a point source. This is the approximation that we're going to make. And also in this particular case, we're going to think of this as a static source. So we're ignoring the possible orbital motion that this source might have around the larger black hole. Okay, this is the approximation that we're making for now. Okay, and then we're also assuming there's a static observer somewhere very far away from the black hole, and this observer is supposed to receive the signal from the source of gravity. Okay, so this is the general setup, and then the strategy is the following. We are going to compute the connecting rays with the spin Hall equations between the source and the observer. Okay, we're going to do this for different polarizations, different frequencies, and so on. And then at the observer, we want to describe the time delays between the geodesics and the spin Hall rays of different frequencies and different polarizations, right? So we want to see how the time delay at the observer is going to depend on spin, on the polarization of the wave and also on the frequency of the gravitational wave. And finally, we're going to use this time delay information to construct the gravitational waveform at the observer. So this is going to be the final step. Okay, so let me walk you a bit slower through these intermediate steps and see what we have. So basically, we start with this setup. We're in a Kerr space-time. This is the Kerr black hole. And next to the black hole, we consider a source of gravitational waves. You can think of this as a point source, even though here, just for the purpose of visualizing, it's a bit more extended, but think of this as a point source. Is many orders of magnitude smaller than this Kerr black hole over here. And then somewhere far away over here, we have the observer, which is going to measure the incoming gravitational waves. Now, this is going to emit gravitational waves. We want to describe this in this ray picture. So let's start doing this. So what we want is connecting trajectories between the source and the observer. So let's see how do we get these. So first of all, we're going to have the connecting null geodesics. So you're going to have one null geodesic shooting like this. You're also going to have a second one shooting like this in general. Now, of course, you're also going to have many other connecting geodesics, the ones which loop several times around the black hole and then eventually escape and reach the observer. Those are there, but for the moment, we're ignoring them just because those are going to be highly demagnified and we don't think those can make a significant contribution to the final effect over here. Of course, we can later analyze them in more detail and quantify this, but for now, let's just focus on the first and the second connecting rays, which should not experience such a large amount of demagnification. Okay, so we do this numerically. What you need to keep in mind is that this is not a straightforward ray tracing process, because basically it's like a boundary value problem. So I'm specifying the initial and the final point, and I need to find the connecting geodesic. So this is like a boundary value problem. And basically you need to do some sort of numerical optimization process in order to obtain the connecting trajectories. Basically, you start here and you shoot in some direction and you see where your ray ends. And then you have to adjust your initial direction of shooting such that in the end you reach the desired point over here. So this is an optimization algorithm that needs to run in order to determine these trajectories. Okay, so this is, if you want, the geometric optics limit. Now we want to go beyond this. So one way of thinking of this is epsilon equals 0 or wavelength equals 0, or you're in the infinite frequency limit. Now we gradually want to turn on the wavelength and also the polarization from 0 to some finite values. And this is exactly what we do here. So let's say I fix one particular polarization, and then I shoot rays at slightly different frequencies, increasing slightly the frequency from 0 to some finite value. Let's say we're going from 0 to 0.1, and we do 50 steps between 0 and 0.1 wavelength. Then I'm going to get this set of trajectories. So for each color, you can imagine there's a connecting ray, and here I have about 50 different connecting rays of slightly different wavelengths. Okay, so these are spin-Hall rays. You see they're a bit different from the geodesic one, and they differ more and more from the geodesic one as you increase the frequency. Okay, we get these rays. Now you can also do the same, but with opposite polarization. So let's say this was S+1, I can also do S-1, and this is going to give me these other rays over here. Again, the color encodes the wavelength and so on. And now we do exactly the same process, but in the vicinity of the second ray N2, and then we get something like this over here. So basically, we have to do this shooting method to find the connecting ray for each frequency or for a range of frequencies and for each different polarization. So we repeat the same algorithm a bunch of times, and then we get this connecting trajectories. Okay, so now what information can we extract once we have these connecting trajectories? Basically, we can focus on what the observer receives, and we can look at the time delays between different rays over here. So for example, obviously I can look at the time delay of this geodesic and that geodesic. That's generally gonna be large. But I can also look at the time delay between, let's say, this geodesic and some particular spin-Hall rays that either lies over here with some polarization or over there with some other polarization. So I can look at time delays between geodesics and spin-Hall rays as a function of frequency. Or I can also look at time delays between opposite polarizations. Now, let's say I look here at this red ray with one polarization and here the red ray with the opposite polarization, but at the same frequency, I can also do this comparison. So let's see what we get if we do this. So basically, we can plot here the time delays as a function of epsilon, the wavelength, and S, the state of polarization. And I'm going to get 4 curves over here. So I get the ones for n equal 1 and S equal plus minus 2. So these two, there are two overlapping. I mean, they're not perfectly overlapping, but on this plot, you don't see the difference. So there are 2 curves over here. And then for n equal 2, again, you have 2 curves over here. These are the time delays between the geodesic n equal 1 and the spin-Hall rays with some polarization and then depending on the wavelength epsilon. A slightly better way of seeing what's going on over here is to go to this logarithmic plot over here. I'm also taking the absolute value of this time delay, and then I'm plotting everything on this logarithmic scale. And then you can clearly see the following. You can see the time delay between the spin-Hall trajectories and the geodesics. And these are always going to scale quadratically with epsilon. So we get this power law over here. And then you can also look at the difference between right-handed and left-handed circular polarizations, and then you get that this scales with epsilon to the power 3. Okay, so you get some lower order effect if you look at the difference between 2 polarizations at the same wavelength. Okay, so basically, after doing all this ray tracing over here, for some fixed configuration of source and observer, then we can basically summarize the results by the following 2 numbers. So first, we're going to have time delay between geodesic and the spin-Hall rays. So this is going to be described by delta t, which is of this form. So it's going to be some beta times epsilon to the power 2. And basically everything about this time delay is summarized in this scalar beta over here. And then we can also look, if we want, at time delay between spin-Hall rays of opposite circular polarization. And then we're going to have a second beta RL over here. So basically this beta and this beta RL summarizes everything about one particular configuration like this over here. Now, we could move a bit the observer, or we can move a bit the source. We can change the spin of the black hole. We can change the radial position of the source. We can change everything we want. And then we're going to get a different configuration. And again, everything within that configuration regarding time delays is going to be described by two different betas instead of the ones that we had over here. So basically, this is a way of summarizing this information. Okay, so beta is, and in particular, we're mostly going to focus on this one. This is a main indication of the size of the spin Hall effect that you're going to get for gravitational waves. Basically, you want beta as large as possible in order to see a larger spin Hall effect for the lensing of gravitational waves. Okay, now a bit more, I can say a bit more about beta. So you want beta large. This is just one ingredient, right? The other ingredient that you want is also a large magnification. So you don't want your signal to be demagnified. In particular, if you would have geodesics which loop several times around the black hole, that's going to correspond to a highly demagnified signal. Basically, you're not going to see almost anything on your detector. So what you actually want is a regime where beta is high or as high as possible, but also the magnification for your signal is high. So this is exactly what we tried to plot over here. So this is the directional dependence of the beta that you would get, and also of the magnification mu that you would get from the point of the source. So let's say we're in the rest frame of the source, and the source shoots rays in different directions. The question is, what's the beta associated with one direction, and what's the magnification associated with that direction? So here we have the plot for the beta. So obviously, since the source is close to the black hole, if you shoot in certain directions, your ray is going to end up in the black hole and you're not going to see that signal. So this white region over here and also over here corresponds to the shadow of the black hole. Okay. Now, very near the edge of the shadow, if you shoot somewhere over here, then this corresponds to rays which graze close to the event horizon. So obviously, these are going to experience a very strong gravitational field, and they are going to have very, very high values of beta. Okay, then the value of beta decreases, and then it increases again on this ring over here. Right, so this is a ring where again we see large values of beta, and then again it decreases because you're shooting somewhere far away from the black hole, and your ray is not experiencing a very strong gravitational field. Okay, so this is the plot for beta. Now we should compare this with the plot for the magnification. How does the magnification of our signal look if from the source we shoot in slightly different directions? So this is the plot over here for the magnification. Again, the black hole shadow. Now, if we shoot very near the edge of the black hole shadow, then these are signals which are going to loop several times around the black hole, and then they're going to escape. But these are going to be highly demagnified. So the magnification is very, very low in this region. So even though we have very large beta over here, the magnification is very low, and we're basically not going to see these signals. Now, on the other hand, what you see is an increase of magnification over here on this ring, which exactly overlaps with the green ring of high beta over here. So this is very fortunate because basically it's telling us that we have directions with high beta, which also have high magnifications. So this is exactly what we want for the signal to be observable and also for the signal to carry a significant spin Hall effect. Okay, so now basically we have all the information. We can combine this, the time delay information or the information stored in the beta and the magnification information in order to build actual gravitational waveform signals and see how they're affected by the spin Hall effect. So when considering gravitational waveforms, if we work in the frequency domain, then time delays are just going to be represented by phase shifts. So if I take some gravitational waveform in the frequency domain, depending on f, and also depending on the state of circular polarization s, then I can write it in the following way. Basically, I have to sum over the different bundles of rays. So this is n equal 1 and n equal 2 in our case. Then I add the time delay as a phase shift, right? So this is the time delay that is determined by beta. This is what we calculated before. I add this as a phase shift in the frequency domain. Then the amplitude scales with the square root of the magnification. This is why the magnification is important. And if we have low magnification, we're basically killing the signal. And then this is my waveform, my reference waveform that I start with. Basically, you can prescribe some waveform H0 at the source, and then you want the waveform at the observer. And this is basically the algorithm that you need to apply in order to construct the waveform at the observer for a given waveform form at the source. Basically, for H0, we can take just some template signal and we can play along and see how these corrections affect the starting template signal. Now, one very, very basic way of comparing different waveforms that we might get is the following. We can look at the mismatch between the two signals, which is a widely known and very widely used measure when you want to see if, in principle, two different signals are distinguishable. So basically, we can compute the mismatch between the geodesic signal and the spin Hall signal, given this formula over here and over here. And then this is going to give us an indication of how different the two signals are, and also a very, very rough indication if, in principle, something like this could be measurable with current gravitational wave detectors. Now, first, let's see how the waveforms look using this formula. So combining the time delays and the magnifications. So we're just assuming some example waveform. This is a waveform for the merger of a 50 solar mass black hole with a 35 solar mass black hole. And then I can compute the waveform at the observer using either geodesics, basically that doesn't change the signal, or it just changes the signal by the magnification. And then I can also look at the signal that you get when you include the spin Hall effect on top of it. So basically, we're going to get two copies of the same signal just because we had two different sets of ray. We had the N1 set of ray and also the N equal 2 set of ray, right? And then there's a significant time delay between the two sets of rays, right? And then within each ray, we get the two different signals. So here you see with the dashed line, you see the geodesic signal. And then with the blue line, you see the actual spin Hall signal with the corrections that you see. So basically, here at larger wavelengths, you see a significant difference, right? And you see this difference slowly fades away as you increase the frequency, right? And here near the merger, the two more or less coincide, right? And here you see a similar effect. You see larger differences at an early stage, and then as you get closer and closer to the merger, the two signals basically coincide. Okay, so this is what we get, and I mean, even without doing any fancy analysis, just by examining how the signals look, you immediately see that there's a significant difference between the spin Hall signal and the geodesic signal in both cases. Now, what we can do is we can compute the mismatch between the two in each case. In this upper case, we get a mismatch of 1%, and here we get a slightly smaller one of 0.7%. So what does this mismatch is telling us? Basically, there's a rule of thumb. If a signal with a given mismatch is observable, assuming your detector achieves a certain signal-to-noise ratio. And basically, I think if I remember correctly, you have to take the product between the magnification and the signal-to-noise ratio, and if that's greater than 1, then in principle, the difference between such waveforms is observable. And with the current state of LIGO, for example, this should be in principle observable because we can achieve signal-to-noise ratios sufficiently large. Also, this is just one particular example, so we can also build other examples where we have slightly larger magnifications up to 5% or 10%, slightly higher mismatch up to 5% or 10%. So then that certainly would fall, at least theoretically, in the realm where LIGO can, at least in principle, measure these kinds of effects. So at least in principle, what I'm arguing is that these types of effects would be observable with LIGO, even more so with LISA. But the actual question is if this sort of mergers actually occur in the universe. So if we actually have systems like this in the universe where you have some very large black hole and then you have a merger of a much smaller two black holes very near it. So in the example that we consider here, if I remember correctly, this is about 10 to the power 5 solar masses. So this is like an intermediate mass black hole. And then, as far as I understand, the astrophysics and the populations of this object is still not fully determined, and it's still not clear how abundant such systems would be in the universe. But now, going just slightly beyond this, I can tell you a bit about the future plans, because I mentioned this in the beginning. So this is what we did, and there are like several assumptions over here. A very, very strong assumption is that this is a static source, and in reality, you might want this to orbit around the black hole. Right, that would be a more realistic scenario. And this is exactly what we plan to do next. We want to include this orbiting motion of the source. You can imagine that you start with the source here, and then you might have a very, very long signal, especially if you go in the regime where LISA is going to make measurements. Then you're really going to expect to make observations of a signal over very, very long periods of time, and then you can think of this source as orbiting several times around the large black hole before merging, right? So this is exactly the regime that we would want to describe. And then we would want to perform the same analysis. Obviously, what you're going to get in that regime is that you're going to see some more or less periodic oscillations of the betas as your black hole, your source of gravity goes around the large black hole, right? So there's going to be some modulation of the beta and also some modulation of the magnification factor. So then basically both these terms over here are going to somehow be modulated along the circular or whatever periodic trajectory you take along the large black hole. And then obviously this is also going to be reflected in the gravitational waveforms, and this is exactly what we want to look at next. Okay, so I think this is all I wanted to say about the lensing of gravitational waves. I think my time's also over. I can mention just briefly, in principle, you can also try to use the same equations to describe black hole shadows with polarized light. But then the main problem is that this is going to be, the effect is going to be very small for the types of radio waves that we observe and for the supermassive black holes that we currently observe regarding black hole shadows. Nevertheless, you can do like some very basic calculations and you can see some polarization-dependent deformations of shadows. So here it's a very brief example for Kerr, where the green shape is the usual shadow that you would get for Kerr for geodesics, and then with blue and red, you see some sort of deformation of the shadow. Obviously, on these images, the size of this deformation is a bit exaggerated just so that we can see something. But in reality, this is going to be very, very small. What ultimately plays the role of epsilon is the wavelength in units of the supermassive black hole where m equal 1. So this ratio between radio frequencies and the size of supermassive black holes, this is going to give you a very, very tiny epsilon, and you would barely see any difference over here. But nevertheless, this might be interesting just for theoretical purposes. Okay, so then I conclude, and basically, I think I already said all I wanted to say. And the main message is that I think, at least in principle for gravitational waves, when we look at lensed gravitational waves, we might have a chance of actually observing this sort of polarization-dependent effects for lensed gravitational waves. Thank you for your attention, and I'm awaiting your questions now.
Thank you, Marius, for this nice talk. Are there any questions?
Yeah, I have a short question.
Yes.
Yep.
Yeah, thank you for the talk, Marius. If you just go to the slides where you presented the black hole shadows, I was wondering because I remember that for the curved black hole, the shadow used to be like it was symmetric around the equatorial axis if you just consider geodesic. So in the case of GSHE, so this symmetry breaks down, right? Am I reading this correctly?
What symmetry? I didn't get that.
So around the equatorial plane, the curved black hole shadow was supposed to look symmetric, but from these images, you could see that it's not symmetric anymore if you consider spin-off.
Yeah, I think what you get is a more complicated symmetry. If you look over here, basically you need to reflect, and also you have to flip the sign of the polarization or something like that. So there's like some I don't remember now exactly, but when I looked at this some time ago, there was like some symmetry like this where you flip with respect to the equatorial plane, and we also change the polarization, and then you recover a symmetry. So there's a more complicated symmetry like that.
Right. Thank you.
Are there other questions? If there's no right now, maybe I can ask a question. Do you know when there's the transition between the spin Hall effect and when you have to start to consider wave optics effects?
So basically, this is still a high frequency effect. So the frequency is not infinite, but it's large. It depends how much you. I mean, in principle, the issue is you can do wave optics efficiently in regimes where the wavelength of your radiation is larger or much larger than the size of the black hole, let's say. You have to work a bit harder to do wave optics when the size of the black hole and the frequency match. And then the wave optics calculation become very, very inefficient when you push, you make the wavelength much smaller than the size of the black hole. So there's like this transition where wave optics becomes very, very inefficient, but then geometric optics and these spin Hall corrections become efficient. So I think in principle, in some common regime, you could try to match them. So still for large frequencies, but not huge frequencies, where at least you do a bit more effort, at least numerically, with wave optics, but then it's not that difficult with ray optics. And then I think you can find like a sweet spot where you try to match them and see to compare results. But in principle, with these ray methods, the goal is to stay in a regime where wave optics effects are negligible. So to be at least one order, maybe even two orders of magnitude with your wavelength below the size of the black hole, let's say.
Thanks.
Mhm.
There's a question in the chat. I just read it. I hope one can hear it. Nice talk. Thanks. Are the spin Hall effects necessarily dependent on circular polarization?
Yes. So basically, let me go back to the equations and I can say a bit more about this. So if you just take the equations as written over here and forget about the value of little s, in principle, you can also have s equals 0 or anything in between plus or minus 1. Now, what would happen in reality is something like over here. So here you start with a beam of radiation, which is linearly polarized. So linear polarized means it's a half and half superposition of the two opposite circular polarizations. So if you compute the little s over here, this is effectively 0 over here, right? But what happens is then after some time, this splits into the two circularly polarized components. So in this sense, the circularly polarized components are the natural components to work in. So whatever wave packet with whatever polarization you would take here, this would end up splitting in the component with one polarization and the component with the other polarization. Now, if you don't start with linear polarization, then you would not have equal amplitudes for the opposite circular polarizations over here, right? But the key aspect is that if you want to use ray methods, so let's say we start over here, we have the initial data for the electromagnetic field in the linear polarized case. If I put this in the linearly polarized case directly in the ray equations and naively set s equals 0, then I get no effect, right? I'm killing this term if I put s equals 0, and then what I would observe with the rays would be like just an average between the two, right? So I would get the ray over here in the middle, which is a bit wrong. Now, what you should always do is you pick your favorite initial data for the electromagnetic field over here, whatever polarization, let's say it's linearly polarized, and then immediately decompose this into a superposition of circular polarized waves. And then for each circularly polarized wave, then you define S and the corresponding ray equations for each circularly polarized wave individually. And then you do this propagation. Then you end up with the correct rays, right? So for one polarization over here and for the other over there. So yes, this is, I hope this answers your question.
Yes, thanks from the chat.
Great.
There's another question in the chat. Thanks for the nice talk. I have two related questions. Which software method did you use to ray trace the waves? And how did you keep track of the different values of n?
Okay, so the different values of n, they just label the different trajectories. In principle, you could easily see them because they're next to each other. Or in other words, in the initial directions that you shoot, you get some over here on the celestial sphere and some over here. So then it's quite simple to see that they're different. Now, the software that we used, we had this implemented numerically in Julia. And there's the code is publicly available. I think if you look in the second paper over here, you can find the link to the code. The code is publicly available. And yeah, we worked in Julia. We did all the ray tracing in Julia. Originally, we wanted to do it with Python, but Python was very, very slow. like orders of magnitude slower than Julia. And then just to give you an estimate, like so here, just to find one connecting trajectory, because you need to do this optimization algorithm. Imagine it's not just like shooting one geodesic. You have to shoot like 50 or 100 times in order to find the exact connecting geodesic. And then you have to do this for different frequencies and different polarizations. So you have to do this a lot of times. So you need it to be as efficient as possible. And then even more when you calculate beta, if you want to calculate beta for different configurations, so this is just one configuration. If you want to do it for 10,000 different configuration or 1 million different configurations, then you have to repeat the same process 1 million times. So that for that reason, we need the things to be as efficient as possible.
Thank you for your detailed answer from the chat. Okay, are there other questions? It seems not. Then let me stop the recording here.